Good morning, students. Good morning, students. I'm now starting with the lecture. So I'm starting with the second chapter. Can you hear me? Hello?
Yes, sir, we can hear you.
Okay. So I'm starting with the second chapter. Now, the name of the second chapter is Magnetic Field in Material Media. That means the magnetic field in due to some material. Now, what you studied in the chapter 1 is the magnetic field produced by a current carrying wire. Now, magnetic field is always produced by some current or a moving charge. So, in first chapter, we have seen the magnetic field produced by the current carrying wire. So, we have used the Biot-Savart's law and Ampere's circuit law to study the magnetic field due to the straight wire, a coil, solenoid, Helmholtz coil, and all other related things we have studied in the chapter 1. Now, in this chapter, we will find out why or how the magnetic field is produced by a bar magnet. So, it is a material medium, bar magnet, or a soft piece of iron, or a copper, or aluminum. Why it is not producing the magnetic field? Why the bar magnet produces the magnetic field? So, this we are going to see in this chapter, that is chapter 2. Now, to understand that, say, the regular current which we make use of, say example, you are studying the current electricity. The current flows due to the flow of the electron, that is a flow of the charges, or in the electrolysis, the current is due to the flow of the ions, positive ions or the negative ions. So now we are going to define one more current. So we name this a regular current. What do you call it? The conventional current as a transport current. It is we'll call it as a transport current. We are simply saying that current. In the current electricity or in the previous chapter, we are simply calling it as a current. But now we are naming it because that's one more type of current. So that current, we call it the transport current because in a wire or in electrolysis, there is a motion of the charges. The charges are moving from one point to the other point. So that's why it is called the transport current. So charges are transported from one point to the other point. It may be in a wire or in a electrolyte during the electrolysis. So we call it as the transport current. Then the second type of current here we studied here is what are called as the atomic currents. See, if you take any matter, see now matter can produce the magnetic field. A bar magnet produces the magnetic field. Why it produces the magnetic field? Definitely it is due to current, but there is no transport current there. There is no regular current. The flow of electrons in a closed path, such thing is not there. Now, a given material, any material you take, it may be iron or a copper or aluminum or any metal. Now, this is made of the atoms. Now, in atoms, electrons are orbiting in a circular path. Electrons are orbiting in a circular path. So now, this since the electrons are moving in a closed path, see electrons are moving in a closed path like this, in a circle around the nucleus. Now it constitutes the current. So the electron circulating in the atom is like a current carrying loop. So it is a current carrying loop. So this current carrying loop should produce the magnetic field. So this current, because of the circulating electron, now what happens is this in this case,
Excuse me, sir.
yes. Hello. Hello. Any issue? Hello. Okay. Now can you see? Hello.
So the screen is not visible now.
Now so it's not visible. Actually, I am sharing the screen.
So now it is visible.
Okay, okay, all right. See, now what I was mentioning is in a current carrying wire. Now that current we call it as a transport current. So that current is called as a transport current because the electrons are taken from one point to the other point. So charges are carried, transported from one point to another point. That's why the current in a wire, or it may be electrolyte. In wire it is because of the free electron, in electrolyte because of the charge ion. So that transported from one point to the other point. So we name that current as a transport current. We name it because we want to define one more current, and that is what is called as the atomic current. Now if you take any matter, it is made of the atom. In each atom, electrons are moving in a closed path around the nucleus. Electron is a charged particle. Charge flowing in a closed path constitute a current. So the electron which is orbiting around the nucleus is like a current carrying loop. So it should produce the magnetic field. Now this current, because of the circulating electron, that is called as atomic current. Now it is different from the transport current because in this case what happens is electrons are circulating in the same region. It is not taken from one point to the other point. So this is another type of the current. Now this current, atomic current, will be responsible to produce the magnetic field in a bar magnet or any magnetic material. So now we have two types of current. One is a transport current. Transport current is a current flowing in a wire or maybe in the electrolyte, and atomic current is a current which are produced by electrons which are orbiting. They are not free electrons. See, transport current is because of free electrons. The atomic current are not due to free electron. Atomic current is due to the current due to the circulating electron around the nucleus. So both this current should produce the magnetic field. So the source of magnetic field is always the current. Okay. Then we know that suppose the loop is there, and see the current is flowing in the loop, current is flowing in this loop. So this is the current carrying wire. Then what will happen is, see, I am saying that this is the loop of the wire. I am calling this is a wire. I'm giving you first example of the wire. Now, this will be acting like a, what is called as a magnetic dipole. See, current carrying loop of the wire is behaving like a magnetic dipole, because what happens is it produces the magnetic field. Since it produces the magnetic field, see, it's producing. If you use the right hand thumb rule like this is the direction of magnetic field which is produced. This is the direction of magnetic field which is produced. If you use your right hand thumb rule, fingers in the direction of current, then thumb will point in the direction of magnetic field. So now what happens is this top face will be north and below face will be south. So it is called as a magnetic dipole. Now for this magnetic dipole, see, this magnetic field will decrease as one goes away from the loop. Field will go away from the loop. But we define another quantity called as a magnetic dipole moment. See, magnetic dipole moment. Now this magnetic dipole moment is direction same of this magnetic field. So again you have to use the right hand thumb rule. If you use the right hand fingers curling around this loop of the wire, then thumb will point in the direction of magnetic moment, and its magnitude defined as current into the area. So current which is flowing into this area of this loop, that is called as the magnetic moment. In vector form it is like this. Magnetic dipole moment is called as the magnetic dipole moment, is a physical quantity and it depends upon the current. More current means more magnetic moment. More area means more magnetic moment. And the SI unit of that is ampere meter square. Current is ampere, area is meter square. Ampere meter square. Now for a given current carrying loop, the magnetic moment is a constant quantity. See, for a given current carrying loop, the same current will flow all the time. The area of the cross section will remain same. So magnetic moment is a constant quantity. But this magnetic induction, this what is we are calling it as a magnetic field. So henceforth we will call it as a magnetic induction. B. B is a magnetic induction. That is a variable quantity, because as one goes away from the loop, the magnetic field will become less and less. So magnetic induction becomes less and less. Now let us apply this to the this electron which is orbiting. So let us consider this electron which is orbiting like this. Electron is orbiting this way. So now this loop is perpendicular to the page. So this part is coming out and this is behind. So from the top, electrons are circulating in the clockwise direction. So it will have the angular momentum. Here we are not interested. If you use the right hand thumb rule, you will get a direction of angular momentum this way, because these fingers curl in the direction of the motion, thumb points the direction of the angular momentum. Then electron being a negative charge, corresponding current will be direction opposite. See, when we write the current here, direction is opposite to the motion of the electron, because electron is a negatively charged. That is what this is a convention which is used. If the charge is positive, then direction of the current is same as direction of its motion. If the charge is negative, direction is opposite to that of the direction of the motion. So electrons are going like this in the clockwise direction as seen from the top. So the current will flow, corresponding current to this electron will flow in the anti-clockwise direction. And now if you use here this right hand rule, the fingers curled in the direction of current, the direction of magnetic momentum will be this, and then the magnetic moment of this the current carrying loop, because of the electron in the orbit of the atom, is current. The current will depend upon the charge. Current into the area of this loop. So here this A is the area of the loop which is formed. You can apply this for the loop. See, magnetic dipole moment, this formula you can apply it to the loop. So same thing we apply here. So what is applied for the loop of wire, that can be applied for the circulating electron in the orbit. Okay. So now what happens is, we know that in a given atom, different electrons are orbiting in the same plane. almost in the same plane, not exactly in the same plane, but almost in the same plane. Suppose all the electrons are orbiting in the same direction. Say, let us say all are orbiting clockwise or all orbiting anti-clockwise, then the magnetic moment, being a vector quantity, they will get added up. Suppose half of the electrons are orbiting in one direction and half in the opposite direction. That means half the electrons are orbiting in the clockwise direction, half of the electrons are orbiting in the anti-clockwise direction. Then what will happen is half of them have the magnetic moment downward, upward, other half will have the magnetic moment downward. So total will become 0. So total magnetic moment of the given atom can be 0 or it can have any other value. And now the electrons in the different atoms, now their plane may be different. So electron in one atom or goes in a circular orbit, another atom goes in a circular orbit, but they may not be in the same plane. Then what will happen is the magnetic moment will be resultant of the two. So the magnetic moment may not become 0. So the total magnetic moment of the atom, see total magnetic moment of the electrons of the atom or total magnetic moment of all the atoms of the material, that is the total magnetic moment of all the atoms of the material, the may be equal to 0 or may not be equal to 0. Now what we consider next is we define another physical quantity. So remember that magnetic moment is constant for the given electron. Magnetic field is not a constant, it varies with the distance. So we now define another quantity. So first is the magnetic moment, second is the magnetic field. Now henceforth we will call it the magnetic induction. Then another physical quantity we define is what is called as a magnetization. So one more physical quantity, magnetization. It is written as capital M and it is a vector quantity. Now, if we consider a small element of the material, if you take a material and if you consider very small element, volume element, then that volume element have the number of atoms, number of electrons circulating. Now, the total magnetic moment of all the electrons in that volume divided by volume, we do it for the element. Mostly why we are doing for the element? Element means a very small volume, because in that element all the atoms may have the magnetic moment in the same direction. That's why we are doing it here. So that's why we take a limiting case. So limiting a delta V equal to tending to 0 means it is a volume element. So the magnetic moment divided by volume, that physical quantity called as the magnetization. So this you have to keep in mind. Magnetization is the total magnetic moment divided by volume. So the total magnetic moment is equal to magnetization into the volume. Now unit of this, the magnetic moment, as we have seen, is ampere meter square. So it is ampere meter square. That is the magnetic moment. And volume is meter cube. See, volume is a meter cube. So the numerator, the unit magnetic moment it is, so ampere meter square, volume is meter cube. Now this will cancel. So what you will get is the ampere meter. So SI unit of magnetization is the magnetization is the ampere per meter. Now this magnetization is a very important quantity in the material, especially material. In a current carrying wire, that magnetization is not important. But in the material, in the like bar magnet or any other material, magnetic material. See, magnetic material means what? One can produce the magnetic field or one which can be made into the magnet. It can produce the magnetic field. Magnetic material like iron, then aluminum, then copper, and so on. For example, wood, plastic, there is non-magnetic material. So magnetic material means, see, the iron is not a magnet, but it can be made into a magnet. It can produce the magnetic field. That's why it is called a magnetic material. The wood, you cannot make it into the magnet. So that's why it is called a non-magnetic material. So iron, aluminum, copper, all these are non-magnetic, magnetic material. So now this magnetization, this physical quantity magnetization is very important in the magnetic material to study the magnetic field produced by the magnetic material. So from the magnetic dipole moment, we have gone to the magnetization. Then earlier we had also considered magnetic field. So this what is called the magnetization is different from magnetic induction. So that B is henceforth it is called the magnetic induction. And one more physical quantity we will define, H. There is the intensity. So we will be defining that later on. So these quantities are required. Then next is say this current density. This current density for a wire. If you take a wire, suppose you take a wire like this, then let us say current I flows and area of cross section of this wire is A, then current density is current divided by area. See, current divided by area, this area of the cross section of the wire. See, for the magnetic moment it is different. That area is the area of that loop which is formed. So that is different. So here is the area of the cross section of the wire. So current divided by area of the cross section of the wire is called as the current density. Now, see, in order to, we try to understand the magnetization of the magnetic material by comparing it with the wire carrying the current, magnetic field produced by wire carrying the current. So now here, see, when the electron is circulating in the orbit, see, electron is circulating in the orbit, then there is no cross-sectional area for that path as such. Now this area of the loop is different. So here it is the cross-sectional area. So now, but what we do here is, we define some equivalent quantity for a magnetic material. That is called as the magnetization current density. So actually magnetization current density for the atomic current, it has no meaning as such, but it is the equivalent quantity that is defined for the wire. So what is done is like this. Suppose the given material, see, given material, this is a material. Let us say it is magnetized. How it is magnetized, we will see that later. It is magnetized means what? It is a net dipole moment. So net dipole moment divided by volume is a magnetization. It has a magnetization. It is magnetized. Now because of magnetization, it will produce some magnetic field at a certain point. See, now here what happens is, we don't give the in terms of current. We consider, we speak for the material. So it is magnetic material. The magnetic field produced by the magnetization of that material. Example, wire magnet. It will produce magnetic field because of magnetization. Magnetization because it is net dipole moment. So now let us say that this is a material. See, this is a material. It produces some magnetic field because of this magnetization at a certain distance. Then suppose we find some magnetic field produced by the wire carrying the current I. Wire carrying the current I. Now what happens here is, we take that the magnetic field produced by this material at a certain point, the value of that is same as magnetic field produced at a certain distance from the wire carrying a current I. Then, see, now what is done is, this is a magnetic field produced by the magnetic material. So now we find what is the current. See, what is the current which through wire will produce the same magnetic field as produced by the magnetic this. Then this current divided by this area of the cross section of that wire, that is called as a magnetization current density. So it is the equivalent to the transport current density which will produce same magnetic field as the magnetization. That means same magnetic field as a magnetization produced in the material. See, magnetization produced in the material. So in the material as such, there is no current density as such. But this current density is an equivalent quantity. We take it as compared to the transport current. Transport current means current to the wire. And we call that current density as a magnetization current density. So this is something equivalent thing. Magnetization current density is something equivalent. We write J suffix capital M. So it is the equivalent current density in the wire carrying a current I, which produces the same magnetic field as that produced by the magnetization of that material. Then the SI unit of that is ampere meter square, because finally what happened is it is defined from that for a wire. So current divided by area is ampere meter square. Now later on we'll show that we have a derivation that this magnetization current density is the curl of magnetization. So del cross M means what? Del cross means curl of the magnetization. That we have to prove later on. Before that, see, so far what you have seen is, is a magnetic dipole moment of the current carrying loop of the atom, electron orbiting in the orbit. Then from that we define what is called magnetization. So this magnetization physically exists in the current carrying loop of the atom. Then we have gone to the current density, magnetization current density. Now this magnetization current density is something equivalent as compared equivalent to the transport current density, something equivalent. Then next afterwards we'll show that magnetization current density is a curl of magnetization. Now to know this magnetization derive this, we require something more. What is called as the magnetization current. So now again we define here equivalent current. Means in this what I have drawn here are circles with arrow. There is electrons which are orbiting in an atom. Now we want to see some equivalent current. Means we define here current that equivalent to the current carried in a wire. So that is what we define. So what we do is, let us say that these atoms are equally spaced. Then uniform distribution is there. And suppose we take some line like this. Now, what is the current here? So what is the equivalent current here? What is the equivalent current here that would flow in the wire? So this is what is drawn here is the magnetic material. This is the magnetic material. So at some point, what is the current equivalent to that current flowing in a wire? So now here what happened is the current here is due to the electrons orbiting on this side as well as on this side. And at this point you will find that these electrons are moving up and these electrons are moving down, up and down. So now at this point that upward current, see the equivalent upward current is equal to equivalent, say now here equivalent upward current is because of all these atoms, electrons in the atoms. So it will be directed upward like this. And this all these electrons on this side, at this point resultant will go downward like this. So upward current is equal to the downward current. So the total current will be 0. So here when there is a uniform distribution of this current carrying loop of the electrons, so that equivalent current at given point in that material will be 0. So we say that magnetization current will be 0. Magnetization current is 0. But suppose if we say that non-uniform distribution like this, on this one side of this line there are more atomic current than the other side, and you will find here that this in this case at least the diagram which I have drawn, you will find that this more current is downward than the upward. This is the upward. More current is downward than the upward. So now what will happen is they will not get cancelled out. So resultant current will be in the downward direction. So there is a magnetization current. So magnetization, what is called as a magnetization current is also equivalent current. It is also equivalent current. So magnetization current is also equivalent current in the this magnetic material. So here if all the atoms are uniformly distributed, then what will happen is magnetization current will be 0. So if the distribution is not uniform, then magnetization current will be not 0, because at that current, because of one side there will be more current, in this case downward direction, than the current moving in the upward direction. So equivalent current will not become equal to 0. So there will be magnetization current. And what will happen is this magnetization current will be responsible for the magnetization of the material. So this is the meaning of the magnetization current is different from the atomic current. Magnetization current is current equivalent to the current flowing in a wire. So that is called the magnetization current. So one thing is the transport current flowing through the wire. Other is the atomic current because of circulation of the atom. And third is the magnetization current. So magnetization current is the equivalent current flowing in the material which is equivalent to that flowing in a wire. So it is the equivalent current. So now next what you have to do is this will show that this magnetization current density equal to curl of the magnetization. So now what you do here is, say I have drawn here the coordinate system x-axis, y-axis and z-axis. See x-axis, y-axis, z-axis. Then I have taken the two elements side by side. Elements means what? Volume element I have taken in form of a cube. This one and this is the next. So it is a volume element. So this volume element is a volume tending to 0. So we will see that side of that is delta x, this is delta z and this is delta y. So this is a delta y because this direction along the y-axis delta y. This is delta x and this is delta z along the z-axis. So volume of each of the element is this one, delta x, delta y, delta z. Then now what I have considered is the two adjacent one which are along the y-axis. Now let us say that first element, the current, see this current is flowing in this direction like this way. I will call it IC. This is a atomic current, circulatory current. IC dash. C means circulatory current, and dash. It is in this volume IC dash. And because of this current, if you use the right hand thumb rule, if you keep the fingers in the direction of this current, then the magnetic moment will be in this direction. But magnetization is magnetic moment divided by volume. So direction of magnetization will be also same as direction of magnetic moment. So that this magnetization will have direction along the x-axis. So if you use the right hand thumb rule, fingers going curl in this direction and thumb points perpendicular to that. Perpendicular means along the x-axis. So direction of the magnetic moment because of that current, circulating current is along the x-axis. So magnetization will be also along the x-axis. So we write m suffix x. So this is a magnetization of the first element m, x comma y comma z. Then what will happen here is the neighboring one, the current. Let us say that current is little more. Here there is no if it is uniform distribution of the atom, there is nothing to prove that non-uniform. So let us say that this is little more. IC double dash is more. So the corresponding magnetization, corresponding magnetic moment, hence the magnetization also will be little more than the neighboring. And how much it is more? This dou mx by dou y delta y, and some higher terms are there which we are going to neglect afterward. Now how you get this? Now in fact this is obtained from what are called as the Taylor series in the magnetism. Taylor series in the mathematics. So there is something called as a Taylor series. We come across in, we take it for granted here, but to tell you that this is written, that increment which is there is given by what is called the Taylor series. Okay, so we will not bother about it. We will take this as equation. So in the neighboring cell or neighboring element, the magnetization will be m plus this plus higher term. Okay, then the x component, see the x component or the magnetic moment. See, we know that magnetization is equal to the total magnetic moment divided by volume. So magnetic moment is magnetization into volume. So magnetization is mx. Volume of that element is delta x, delta y, delta z. This is what I have mentioned. Delta x, delta z and delta y. Volume. Length into breadth into height. So length cube it is, because it is a cube, length cube. So this magnetic moment, magnetization into the volume. Now this is from the definition of the magnetic moment. From the definition of magnetization. Now here we write from the definition of the magnetic moment. So this is a magnetic moment. So current into area. So current here is IC dash. What is the area of this? The area of this is, see, area of this square face which you can see in the front, square which you can see in the front. This length is z, dz, and this length is delta y into delta z. So this is delta z and this is delta y. So it is delta y into delta z. So this is what we have written. This we have used the definition of magnetic moment. So this is the definition of magnetic moment. Current into area. So area of this is delta y into delta z, and this side we use the definition of the magnetization. Then similarly, x component of the magnetic moment of second element, this second element, x component, this is the magnetization into the volume. Then definition of magnetic moment we use current into the area. So this is of the second element. Then we subtract 2 minus 1. See, this is what we had done on the previous 2 minus 1. We subtract, and when you subtract, you get like this. So here what happens is we subtract larger minus smaller. This, then this. Not this one. This and this cancel. This is there. Huh? This is there. Okay. So that cancels. So now what you get is IC double dash minus IC dash. IC double dash minus IC dash. Then we have written here, what is remaining there we have written here. Then this and this cancels, and what we get on this side is this one. Now this IC double dash minus IC dash. See, IC double dash minus IC dash. Now this IC double dash, see, along this edges of these two elements, it is downward, and here this is circulating like this, upward. So this IC double dash is greater than IC dash. So resulting magnetization, the magnetization current is downward. So what we now write, this one is the magnetization current, that is downward. So IC down we write, and we get IC down is like this. Then you consider next two adjacent volume along the x-axis, along the x. Another we take like this. We will not draw the diagram. Volume like this. This one. So along the x-axis, see, we next consider two adjacent volume element along the x-axis. Then if you find the y component of magnetization, y component of the magnetization, you can find out y component of the magnetization, because it will be this side. Say these two elements if we take, then magnetic moment will be this side. Then similar to this, what we will get is this, instead of mx we will have the my, dou my by dou x, delta y. This is what you will get. Okay, this is IC up. Okay, so now this is called as magnetization current. So it's not a transport current. Then we find next, what we find is this net current in z direction. Net current IC up minus IC. Now here what I mentioned is this the first one, then IC down you will get here, and because of these two elements, IC up you will find. So now both this current along the z axis. So resultant current, see the resultant current with the difference of the two, and that's what you get here, IC up minus IC down. So now this is a net current in the z direction. So in fact net magnetization current. So what we have written here, magnetization current. Then effective area of the current element, as I have mentioned, is delta H delta Y. So this is the magnetization current divided by area, that will be current density. Z current component of the current density. This is Z component of the current density. See, this is the magnetization current. magnetization current. In fact, it is the equivalent magnetization current. And if you divide it by area, so when you divide it by area, this and this will cancel. So what remains here is this one, dow my by dow x minus dow mx by dow y. So that is z component of the current density. So we write Jm suffix z. It is a component. Similarly, in same way, we will not prove that, but you can say that x component of the current density suffix x will have this component and y component will have this term. Then the resultant this current density, magnetization current density resultant. See the x component into I cap, y component j cap, and z component to k cap. Now this is nothing but say if you try to combine this, if you try to substitute here, I'm not substitute here. If you try to substitute this, then this, and that will turn out to be the component of the cross product. And we can write this as a cross product of del and m. See, if you substitute here, delta m suffix x, this one, then substitute here, delta j m suffix y, then substitute this one, they are nothing but the component of the cross product of del and m. So this we can write is a del cross m. So we have proved that the Jm equal to curl of m. So magnetization current density is the curl of the magnetization. Okay, so that is the derivation for the this magnetization current density. So remember that this magnetization current density is something equivalent to that of the current carrying wire in the material, and this magnetization is actual thing in the magnetic material. So we can write this from this we can get, from magnetization we can get magnetic current density. So now what will happen is similarly we can get from here magnetic field. Okay, so all these things are done in magnetic material. Magnetization is studied with respect to the current flowing in the wire. So this completes this part, and I'll stop here and I'll continue on Thursday, because tomorrow and day after tomorrow is the holiday. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Okay,
sir.
welcome.